Hello, Paige. How are you?
Hi, Melissa. I'm well, thanks. How are you?
I'm very well, thank you. Is Catherine? She's got the heads up on how she comes into the live stream, right? Is that okay?
Catherine should be able to come ASAP. Yeah.
Brilliant. Okay. Well, it's great to have you here today. Where are you currently?
I'm in Barcelona right now. I'm in one of those kind of like dark little inner courtyards, hence the yellow light. But yeah, it's a rainy day, but it's been amazing.
Uh, well, we've got thunder coming in here, so I'm hoping that we don't get a major electrical storm right in the middle of the live stream, but hopefully we'll be fine. So we'll just wait for Catherine to come in. I can see we've got some people joining us.
Very thematic. I like it.
um, for those that don't know the series, Biofutures is a series of conversations with seminal thinkers that are working at the edge of biomaterials, of biodesign, of biofabrication, among other biofields. In the first series, we explored these fields as applied to the built environment. And in this series, we are exploring these fields as relate to the body, to health, and to well-being. Hence why electric skin simply had to be in the series. I might start off with your intro as we wait for Catherine to join. Now, I'm not sure. I haven't seen a request from her yet, but
Disclosure is that Catherine is in Mexico and often in places absolutely off the grid. She does often have like connection issues that, yeah, we'll if not there, I'll do my best. So she is the material expert, but she knows this, yeah. So.
Oh, brilliant, excellent. So, Paige, how did you get involved in the field?
Gosh, for me, it was in Trinity College Dublin. I don't know if you know the Science Gallery there.
Yeah, it's very well known.
That course called the Idea Translation Lab, and that year it was synthetic biology, and we were all paired up with biohackers that were our mentors. And actually, my first project in that field was a tattoo, a biofilm that could read your nutritional deficiencies. Obviously, a speculative project that now, kind of 10 years later, is feasible. I think I've seen projects that do exactly just that. But for electric skin, it was through the Biodesign Challenge. They ran a sprint about 2 years ago that was for hobbyists and professionals. And the four of us that are involved in electric skin were all kind of hobbyists that were interested in biodesign. And we got kind of smushed together on this subject of how do we redesign electronics. And just we found this piece of research. It was called The Mud is Electric. And that was intriguing to us. And that's how we discovered all about Geobacter and that bacteria and its capabilities and the research done on the proteins that it creates that itself generate electricity. So
brilliant. And so that's when you all met. That's how the founders. And did you work together on the projects that you were creating for this, or did you just meet on the program?
We met through the program, but I think we'd all heard about each other through just in general the bio community, the MIT bio community. You know, they have that big conference every year. And so it's a very small world, isn't it? It's a very niche world where, I mean, I've heard of you, of course, years ago without ever meeting you, but following your work. So that sort of connection, distant but niche.
Yeah, yeah, and it's brilliant because you're four female founders, and I love the equity between you. That is, I think, very representative of the biofields more generally. But it's really great to see four women. What do you each bring to the table? What are the unique sort of elements that, as a team, combine to make the magic happen?
Yeah, that's a really good question. And I think I was listening to one of your other lives, I don't know, a few weeks ago, where you were talking about the fact that in biodesign and in biotech in general, there are so many women and how interesting that is. But we've got a very complementary set of skills. So Catherine is the material expert. She works with lots of different materials. Right now, she's applying her knowledge with alginate to electric skin, and we're using mostly that. But she works a lot with mycelium and kombucha and actually trying to, or bacterial cellulose, sorry, and trying to interlink those two to make it stronger. So just kind of understanding the material properties of thin films and flexible films, and bringing that to which of those materials is going to be conducive to the environment that we need for the proteins to actually make the electricity. We have Sequoia, who's just given birth to a little girl, and who's on this journey with us, but just kind of, it's so impressive how she's juggling everything. But she actually is an expert in synthetic biology, and she was able to help us kind of scale up the lab processes that they had started to uncover at UMass, but weren't incredibly efficient yet. So we did that over in BioCurious in the US on the West Coast, just kind of in a community lab, basically, with very little means. But that was great that we were able to do that, because now it means that we're going to be able to grow lots of proteins and share those with other researchers who are interested. And Nada is based in Qatar right now, actually, and she's an incredible designer, and she's been amazing at basically illustrating a lot of the concepts that we're working with and making them kind of poetic and I think attractive looking as well. And I have trouble describing myself, but I'd say hopefully I'm the glue coordinating us all and making sure that the energy stays there and making connections as well. Just kind of a nerd about biodesign, but not necessarily having the skills to kind of make the science happen.
Yeah, and that's so important, because so often you find that with brilliant projects that have enormous capacity, you don't necessarily have that individual on the founding team. And that is the person that can make the difference. That can be the difference with one of these startups, between actually knowing what an opportunity looks like, being able to sort the wheat from the chaff, actually recognizing, well, this is where we need to put all of our limited energy, because you invariably have only so much time and resource. And then this one we park. And so that's your role. So it's great that you've got that. And that's, I think, one of the reasons that you stand out, because you've got this incredibly dynamic 4-lady team. You might, I think you joined on the Veronica Rana session. Not sure if you were in it when we were talking about this, but we were talking about the fact that when you work in different parts of the world, you can find you get different advantages and disadvantages. When we think to the startup community, and particularly anything sort of tech, as it were, there is this general impression that the US is a much easier place in some respects to launch ideas, because there is an appetite, there is an energy. But your setup's really interesting, because you've got bases around the world. You've sort of got this global community. How do you find that affects the startup in terms of the project, in terms of pushing it forward? What do you think are the advantages and disadvantages of that?
Yeah, I mean, again, that's a really good question. There's so much to unpack there. But let's see. I mean, the first thing is actually it does make things slower, because we're not affiliated with any kind of university to start with. That limits a lot of our resources. We have to operate on basically where the community biolabs are, or where we can find collaborators that have machines. So we have to rely either on our networks and collaborators that we have in each of our different places, or in the US, there are those kind of community biolabs where it's easier to get access, and even with little levels of finances, kind of get the machines that you need to do the research. But that still means that Catherine needs to send us her materials from, maybe Mexico or Canada, and then I need to receive them, and then they need to be sent to another place potentially to do the plasma etching. And that takes a lot of time and a lot of shipping money. I mean, this is very real. And so it makes it very complicated, but at the same time, in each of our places, there are different sources of funding. There are different opportunities for collaboration, and we each have our communities in our places that mean that we can make things happen differently in each place, basically, which also means that we have to make choices. Okay, well, which avenue do we go? Is it this more artistic route? Is it this more scientific route? Like, where do we have contacts? And right now it's actually been incredibly busy, and we're finding that, and I don't know, so I've just had a conversation actually with someone who's more in this biotech world, or but none of us have a PhD, for example, and for investors that really limits what they're willing to kind of put money in. So do we take a more of a coordination role where we kind of gather communities of practice to do this research with us, or do we go a product route? Those are the sort of questions that we're asking ourselves right now. But if we wanted to go a more product route, then we'd all have to be in the same place, really. So yeah, it is interesting because I think that the future is decentralized research in a lot of ways. I used to work for a company that did that. But at the same time, it does make things slower and more limiting in terms of fundraising and being able to do the work.
Yeah. And it strikes me that, you know, your position is very similar to a lot of other people in this community. There's quite a lot of migration, and although generally in STEM and in the arts, you do find people moving around quite a lot, whether or not they're in commercial or they're in academia, but this is a very sort of migratory community. I mean, most of the people, well, I think I'd be hard pushed to think of somebody that isn't working across nations in terms of their affiliations, their partners, their clients. And it's interesting at the moment because although lots of lots of countries are talking about this, they recognize that this is a big frontier. There's so much potential here, but we are yet to see, certainly I think in Europe, we're yet to see that infrastructure in place. So it's very embryonic. And I feel that where you are right now is where a very many are. It's trying to sort of make that call between, well, do we take this into research or do we actually go into startup, etc.? It feels with your project to me like more like a startup, and I think that's a good thing because I think now is a good time to have options. But it's very interesting, and I think a lot of other people that are working in this field could sort of take a leaf out of your book through this working through collaboration. As you say, theoretically, the way that you're working is not new, in that tech startups have been working distributed globally for like 3 decades. But in this, I mean, that to me, shipping, getting those samples, getting that stuff around the world, that seems a headache. So all credibility to you as a team to be working that way, because that is no mean feat. Yeah. That's a major challenge in itself.
Thanks. And I think, I mean, for me, one of the most important things that we're doing at this point before we're able to really progress the research is being able to tell the story. Because, okay, so we found this incredible research paper that finds out these really interesting things about these bacteria and these proteins and this capability to make electricity in this very, very interesting way. But at UMass University, they hadn't, you know, I guess I don't know the academic world very well. I haven't been in it much. But, you know, they didn't have the means or the funding to continue that research, essentially. So they found this out and they moved on. And what I think we're doing that's important is kind of really starting to spread that wider and say, okay, hey, we're going to kind of build the infrastructure for this to be more easy and more possible. We're going to grow the proteins and we're going to be able to send them around the world for people who are interested in this and who have more skills than we do as well, to kind of come on this journey with us and uncover a lot of different applications. But realistically, any of the applications are going to come out in maybe, I don't know, 5-10 years. Anything useful or scalable. But I think what's important now is to start telling the story of what's possible, and because I think biodesign and biotech are, again, super niche worlds, but that shouldn't be. We all need to start believing in the power of things to be grown in like bacterial worlds, to start creating bigger worlds that we can use in our daily lives. And I really believe in our kind of approach in trying to make that more accessible. And I don't know if we're succeeding quite yet. I don't know if my friends understand what we're doing. But I think that's really, really important. And that's one of the main core things that we're trying to do now, as well as going the startup or product route. We'll see.
So for those people that are listening, some of them will know your work, others won't. in a nutshell, what at the moment are the core areas, if you like, of application that you are exploring? What sort of problems are you trying to solve with your work?
Okay. Maybe I can start at the very, very beginning.
Absolutely.
There is a bacteria in the ground. It's called Geobacter sulfurreducens. Not exactly sure if I'm pronouncing that right, but I will just. And it grows in anaerobic conditions. And actually, there's a lot of bacteria like this that grow all around the world in anaerobic conditions. So in ponds, in deep sea trenches, anywhere there's not oxygen in the soil, not a lot. And what these specific bacteria have done is that they've created tiny little threads made of protein that come out of their bodies and that are able to capture create electricity, and they do that to capture the metals in the soil so that they can feed themselves. And there's this group of scientists that found out about this bacteria and that decided to kind of extract those proteins and just use those proteins. And they put them on a little piece of glass on a very specific polymer that has captain, I think. And they were able to, by basically dropping these proteins in like a specific thickness and with a humidity gradient, that means there was more humidity at the bottom than at the top, and this is at a micro level, of course, they were able to generate electricity. And what's really interesting about this electricity, it's called hygroelectricity, apparently, and it performs quite well. It performs with just the simple humidity in the air, so 40% is probably what you and I are both breathing right now. But it also actually, if you put the conditions right, is able to generate continuous electricity. So what they did is they connected a bunch of little cells with these proteins together with a capacitor to kind of even out the flow of electricity, but they were able to light an LED. And that's what was really interesting to us. Obviously, if you light an LED, what else can you light? If you just kind of amplify the scale of those things, how much can you power? But we were really interested as well in, you know, if we're growing bacteria and extracting the proteins, then it shouldn't just be on a piece of glass or on a synthetic polymer. It should be on a biomaterial, right? So that can degrade back in the soil. What if we created a source of electricity that was growable, that was compostable, that was beautiful? And that's what we're trying to do. And now I'm trying to remember the exact beginning of your question, because I've given context, but I don't remember going.
You've explained essentially what you're working with. So you've explained the medium, if you will, so how you're generating the electricity.
Yes, we're going into the application.
And how do you see this being applied? What, in terms of, you know, the sort of applications do you see, both in terms of scale and possible, if we were to think particularly in terms of products, what sort of things do you think could come from this?
Yes, I mean, so many. Of course, at this precise moment in time, we can only aim for small amounts of power. So things like sensors, things that are lit with minimal amounts. So, you know, we're thinking tiny little lights. We're thinking sensors. We have some scientists in the community that propose that there could be entire kind of electronic pieces that could be made out of those proteins. So like capacitors and connections made of that, which would be a really, really interesting thing to do, which probably we won't. But also biomedical devices. Alginate in general, which is the material that we're working with, is heavily used in the biomedical industry. So, you know, what if we could create beautiful casings or diabetes packs that kind of worked with your body and that still kind of provided the functionalities without kind of being any sort of toxic to your body? That would be wonderful. What we'd imagined kind of in the future is if we were able to scale this up to kind of massive amounts, you know, could we coat our walls and harness the humidity in the air and kind of power our home, our smart homes? That would be incredible. But then, of course, and what this conversation is really about is, what about the future of fashion and textiles, which is what Catherine works in a lot. And there's so much going on today with smart wearables and smart textiles, and where that could go is in so many directions, right? Like, can we power our phones just by kind of wearing these kind of electric skin t-shirts or bodysuits, but also can we, Geobacter has been used as well as a sensor for toxic environments. And so, you know, could we create clothing that lights up when you come into a space that's too polluted in a specific way? So, I mean, you know, those are 5 or 6 things already.
My business is going
it was
towards the sensors for sensing harm, sensing health. That's where I'm thinking if you were pitching this to investors, that's going to be your area. And that's actually incredibly exciting because you, sort of when you think about the future, so what sort of things could these materials be sensing? It strikes me at the moment, a lot of people have a smartwatch. I've got a friend that's got a heart condition, and she relies on her smartwatch to basically make sure that if she starts going to cardiac arrest, then a warning is going to go out and somebody's going to come and save her. It strikes me that, you know, you could have interventions, couldn't you? You could have the signal go out, as you say, for diabetes, for stroke, maybe, really anything to do with sort of cardiorespiratory system. It strikes me for viruses, sensing viruses, because your problem there is you've got so many pathogens. But then again, I mean, we know, for example, thinking about North America, the climate is that the fact it's changing, it's releasing certain pathogens. So we know certain toxic pathogens are in certain environments. So I'm thinking this could be sensing that. And I guess the other thing, one of the conversations that has sort of been coming up about sort of energy is that historically, when we think of energy production, we think about great big installations, we think about big ugly power plants, or more recently, we might think of enormous offshore wind farms, these kind of things, massive, great big arrays of solar. Actually, some of the most cutting edge research and ideas are looking at low voltage. It's, you know, Rachel Armstrong looking at her 12-volt home where as many things as possible run off that. And for people that are used to the idea that you run things on high voltage, that's kind of a mind blowing. But actually, as a designer, when you bring in the design element, you can, through engineering, bring that energy need right the way down. Mm-hmm. And I'm thinking for sort of medical, you know, if you think about the size of a modern pacemaker, I mean, they're barely even a centimeter high, aren't they? They're so tiny.
Exactly.
I'm trying to look around for something that's small, and I haven't got anything, but they're minuscule. And I'm thinking your work, potentially one of the applications, could realistically power these critical life-saving interventions, both in day-to-day use and obviously in situations where people are going into, let's say, polluted environments. Mm-hmm. We've got chemical weapons, we've got bioweapons, we've got something nasty going on there. We need a warning system. It strikes me that that's a huge potential application for this.
I think so. And I mean, if we're kind of going speculative as well, like one of the things that I was working with in the past is like maybe those are kind of signs of identity and things that you're choosing to wear for their aesthetic. And I think that's also the story we're trying to tell with electric skin, is how do we kind of cultivate those odd kind of bacterial aesthetics that are new, and that signal kind of, okay, this, maybe I do have this kind of weird biomedical condition, whether it's pacemaker or diabetes, and what if that was a sign of pride? Now I'm wearing this strange material in my body that's helping me do the things that I need to heal or to continue functioning. But it's also a fashion statement. Maybe that's a silly thing to say, but you know, what if we lived in a world like that? That might be nice. Absolutely, because the potential of these proteins is that, yeah, they're non-toxic and they adapt, and they're not weird, strange materials and metals that you're putting into your body or on your body for long periods of time and that are contributing to. And again, I can't talk too much about that because I'm no expert on biomedical devices, unfortunately. But I think where this research could go is definitely a hugely, yeah.
I think it dovetails also beautifully. You know, my own research project looking at how we build resilience to major wildfire events. A major part of that is an ICT system that is basically mimicking the natural signals that we find in the natural world. So, I mean, today it's commonly called the World Wood Web. The the fact you've got these mycorrhizal and root networks, but actually the whole environment, every plant has these sensors. We can now read these sensors. But nonetheless, if you're actually going to connect that data, the sort of is being sent up to the processors, that you're actually going to then feed into a system to help warn you in what is a very terrestrial, potentially a very analog way. Well, have we got the conditions for a wildfire? Is this area more likely to burn? Is that? It strikes me again that what you're working on is perfect, because it's the right scale. In that environment, you absolutely don't want big electricity surges. You want micro energy, just enough to power the sensor or the actuator or whatever it is that is part of this big system. So I think it's hugely exciting. I mean, I can see lots of different organizations, civic and corporate, being really interested in what you're doing. How much, you've obviously mentioned that you work with a number of partners, obviously because you're working independently. I mean, effectively, I would say that you are, well, you're sort of not just independent scientists, but you're an independent research project, effectively. How have you found that the process of trying to get the knowledge and the resources that you need to actually scale this, how easy or hard have you found that? What have been the big challenges, and what have been the sort of the easy breaks?
Oof. Yeah, I mean, lots of bottlenecks. I would say for the moment we've had a lot of help and support, and that in a few months we're going to be able to truly have collaborators, because we can actually start distributing the proteins. But I mean, the big win at the kind of beginning of the year was basically we got just a small pot of funding from the European Union. It's part of actually much more of a art and design grant scheme. But it was enough to start to go to this community biolab in the States and kind of try growing the proteins in larger liquid batches, which was a huge win, because that's the main bottleneck, actually. How do we get these proteins? At UMass lab, at UMass University, they're actually obviously very overwhelmed. They didn't have the capacity. So they shared with us their plasmids and the bacteria that we needed to grow this. And, you know, they've been incredible collaborators in that sense. We've been able to kind of call them when we were having issues or not understanding what's going on with the material or with the proteins. But that's the big one, is how do you get those proteins? And then shipping them is also pretty difficult. I mean, it's proteins, it's still kind of a biomedical, it's a biotech thing. So there's specific rules for shipping it across the countries. And so that's a difficulty. But then the thing is, we've been working at it in a very DIY sense. We haven't had access to the amazing machines that you find somehow in universities. So for the moment, we're still kind of stuck out of that, and we're going to need to create partnerships with places that have the machinery that we need. But why we need this machinery is that this is all happening at a very microscopic level. Right now, we're doing it on alginate, but what alginate is it's a seaweed material, and it obviously, when you look deep into it, it has massive crevices. And what we need for the proteins to start making electricity is for them to be on a plane surface at the microscopic level and be interlinked in a very efficient way. It's still working. We're still creating voltage from, you know, the proteins on the mountains of alginate. But obviously, to be much more efficient, if we had a plasma etching machine, or if we had access to an amazing printer of gold electrodes. And so because it's micro manufacturing, it's difficult to get access to those. So once we're able to kind of get Sequoia back to the States and, you know, send her back to the community biolab to start our production, our intent is actually to create a little toolkit where we have little vials of proteins and a micropipette, maybe some of our material, and maybe our toolkit that we've written as well, and start sending that out to people that we've identified really want to collaborate, really understand this type of electricity, really have an interesting proposal for how to kind of go about this, and you know, start really kind of going that community research route as well. Because I think we understand that we have an interesting set of skills on this team, but people have access to incredible facilities where they are as well, and we'll be able to take this further. Then we can, or just altogether we'll be able to go faster and cheaper. So yeah, hopefully that answers that question.
Yeah. So actually, certainly, you know, at the level of the research, you've generally found that this is going, you know, pretty well. It's going pretty well. You've had the initial help that you need. When you think to scaling this, obviously it's very difficult at this early stage because you've still got a lot of things to work out, a lot of questions to answer. But when you've thought about where you might take it and how you might actually make this something that could be produced, certainly at a sort of scale that would be accessible, not necessarily ubiquitously, but to particular niche markets, how do you envisage that? How do you envisage this process being sort of, if you like, putting into production?
Yeah, I mean, it's a difficult question because at the moment, the big thing that we have to do is uncover the most sensical application, the one that could hit the market the quickest. I mean, thinking in startup terms. And so again, like my sense is that it's in biomedical devices. There's a lot of money in that industry and there's a huge need. But it could be something else. It could turn out that actually what the research leads us is an entirely different direction. So it's hard to say. I think right now it's really kind of like a gold rush to exploring what works the most. And actually, maybe it's not even on alginate. Maybe it's going to be on another material. And the other interesting part is what the connections are between the little cells. Is it graphene? That would be incredible because it's very compostable and not necessarily need for extraction. But right now it's been performing much better on gold electrodes. And we've tried copper, but that kind of rusts because there's humidity involved. And so there's so many different questions to answer. So many kind of things to figure out, and we really need kind of an electrochemist actually to put their brain on this, because and no one really understands this chemical reaction that's going on. There's been a lot of theories and interesting theories that are out in a lot of great scientific papers, but it hasn't exactly been proven yet. We know that it's working, we don't exactly know why. So yeah, I mean, again, really difficult question to answer. I think right now what I'm just trying to do is like a massive push on research, just telling people this exists, that now it's accessible because we can grow these proteins faster and we can send them around. But within the next 2-3 years, it's really about kind of just probing a lot in a lot of different directions. And that's my sense. But maybe someone else has a different kind of opinion.
It strikes me that, you know, Imperial would probably make a pretty good partner for you, because I think they would definitely have some of the talent that you need. Probably Cambridge, you know, certainly in the UK. I think, as you say, you know, what's interesting about this, I mean, actually, when we think about the series, I guess in terms of, you were saying about sort of PhDs being a bit of a barrier to trying to get sort of some funding, some investment. I guess if this series, probably about only actually a third, I'd say around a third have a PhD or are in the process of attaining one, and many actually don't. And there's a very specific reason for that. It's because this is such an emergent field. Even if, you know, Nicholas Negroponte and lots of people were theorizing this, you know, decades ago, the reality is that right at the edge of innovation, this is not a scenario in which, you know, you have, well, certainly you don't have many kind of major players in many industries that are working in this. So it's not as if you're necessarily going to get a corporate sort of sponsor or environment to kind of scale this.
Yeah.
You know, it's one of those things. Certain things work better for a PhD and others don't. And my sort of sense is, if you were going to, you know, do that, you'd be writing your own program anyway. You'd probably actually be getting the research funding anyway, because it's so at the edge. So I don't think it's I think it's a shame actually if investors are not getting behind you because of that. And I think that you could compensate for that through your partnerships. So I think you're doing just the right thing you know, right now. But I do think you probably, by the sounds of it, yeah, I think you probably need a couple of universities where you've got, you know, the particular talent that you're seeking. And certainly, you know, Imperial are very collaborative with RCA and, you know, some of the other London institutions. And I'm sure that there will be folks there that will be really interested in what you're doing. So if anyone from Imperial is watching, get in touch with the Electric Skin guys. You know, they've got something exciting going on here. And thinking to...
we haven't, like, we're just about to start that journey of really looking for those collaborators and making that happen. So like what I'm saying about investors is, yes, I fear that it might be slightly difficult, but who knows? Yeah. But also I think that, like you said, it's a shame but at the same time, I think there's a lot of things that go on behind doors in industries that I don't know about. I mean, in pharma and in the biomedical industry and in other things, I think there's a lot of funding that goes into places where there's actually already the infrastructure and there's already the minds putting their work at that. And so it's also a problem of kind of access and kind of and collaboration within, kind of like between industry and academia and just whatever we are, right? Kind of independent research groups. Like if those connections were to be made in an easier way in this world right now, I think that could be.
And I'd say whichever route you're going to go, I mean, on this, the unfortunate thing and the challenge of this field is that IP is important, particularly if you're going to go private, you know, for private investment. You've got to get your IP nailed. So you probably, have you got mentors yet that are helping you navigate that space, knowing... Yeah, that's really important, because that, again, that I would actually say is going to be a bigger difference for you when you come to getting investment than whether or not one of you has got a PhD. You know, if you've got your sort of IP journey strategized, if that's all like laid out, then that's
right.
A big... Looking at this sort of the rest of this whole sphere, looking at biomaterials, biodesign, what are the other kind of areas that you would like in the future to sort of maybe apply this to? Obviously, we're looking at the body and health and well-being, particularly in this series, but how else can you see electric skin in whatever configuration it manifests? How else can you see that applied in the physical environment?
Yeah. So, I mean, that's what we spent a lot of time thinking about. The way we originally conceived it for the Biodesign Challenge was like the case for a phone, right? What if we could, and the question we're posing is, you know, what if we could grow all our electricity, basically? What if our electricity was not extracted and it was grown by bacteria? Because the issue is that all of our forms of, okay, maybe not all of them, maybe not some of the newer ones, but everything that we have, even renewables, are based on really on sustainable practices, actually. You know, solars rely on a lot of mining, and wind farms are just these massive monuments that just cannot be recycled. And so what we're trying to say is, you know, maybe there's another solution, and let's really explore this. Let's go there. But so essentially, I mean, the vision would be to replace absolutely everything, right? You know, in complement with other forms of groovy power that we might have not thought about or that are in development. But what's interesting about this specific form of electricity is that it relies on the humidity in the air, and that can be found absolutely anywhere, even in deserts where there's approximately 20%. And apparently it still performs there at 20%. So that's really interesting, because that cannot be said about wind power, about nuclear, about this, or about geothermal, about a lot of different things. So the opportunities for this form of power to be absolutely everywhere, to power your homes, to power your new smart clothes that also have some sort of screen going on here, to maybe not power entire cities, but actually that's what one of the other companies in Barcelona that's doing that, that's working with this bacteria, is doing. So this whole thing is, you know, the concept of the microbial fuel cell.
Yeah.
And that's
other previous biofutures with a couple of researchers who are exploring that.
Perfect. I mean, that's one of the bacteria that's engaged in that process, right? And you know, there's people working on how do you light up entire cities with soil or with this form of power. And so it's about connecting, like creating interconnected systems of cells that have that capacity, like you were suggesting with the wood wide web. What if there was, you know, electric skin wide web? But it's kind of a hard question for me to answer because in my mind, the possibilities are endless. Where there is electricity, there is potentially this. Where there are electronics, there is potentially electric skin as a coating or as an internal kind of battery. And we've had a lot of trouble actually defining what this is. We're saying self-powering material. Some people have described it as a battery, but it's not exactly that either. And so maybe it's a whole new concept.
I like the whole concept. I think I would run with that. A lot of things at the moment, because it is splicing up different systems, and that's one of the big challenges, isn't it, of this field. It's, you know, a material is also performing at the level of fabrication and engineering, and there's all these sort of crossovers. So, you know, although we live in a siloed world, and sometimes you will have to try and create a category classification, but it's actually, we're doing that because we kind of have to. I mean, realistically, the complexity, the connectivity is really, really tight. So, you know, it's more about sort of creating a language that helps some people to understand, but in reality, at the level of practice, you know, you're sort of working across what are technically different fields and different disciplines.
And the potential as well, I'm sorry, I have to mention, is that, of course, we're working with Geobacter and their protein, but we're actually working with E. coli that's been engineered to express this protein. But many other types of electrochemically active bacteria have been discovered. And we don't know how to work with them. Like when I say we, I mean humans, know how to work with them quite yet. But there are things like cable bacteria that are just bacteria themselves that can kind of link between each other and create massive, almost visible to the human eye, basically circuits, because they can transport electricity through their body. And I guess this is a whole new field of discovery, electrically active bacteria in general, and how they work. And I think there's tremendous potential there. And if that could be known more and people could realize that research and it could be spread wider and better accessible to the general public, that might also be really interesting and give results that I can't even start to imagine.
I think it struck me throughout, well, this series and the last, and I guess working in this field more generally, I think one of the reasons that women do particularly well, I mean, a number of women have seminal ideas, it's because women do tend to think about complexity. There is this sort of multitasking of the mind wherein you're thinking about several different things at once and you're creating comparative balance. Obviously, not every woman is the same, you know, we're all different, but women tend to be very good at that. And I've noticed sort of in the startup world that whereas a lot of men pitch the back of the envelope, it's sort of the, you know, back of the beer mat is the strap line, it's X and it's going to solve Y. That doesn't tend to be how women think. Women will tend to sort of think of the problem in all of its complexity, and then they will tend to, if they're pitching, there will be a much more complicated, there'll be a lot more going on with the way that they're effectively trying to answer a question. And that's perfect for this field because it is really complex.
Yeah.
Yeah, it's the way that
the other things that you've mentioned in some of your other lives as well was the kind of the ethics of all that, right? We're working with bacteria, but we don't know what that means and if it is ethical or not, because we cannot communicate at this point yet. And I think going into this project, that was also one of the things that we really deeply wanted to think about. I mean, what does it mean to kind of cultivate a bunch of bacteria, extract their proteins, and then kill them off? I don't actually know. And I won't know for a good few years. But yeah, maybe that's one of the other kind of strands of thought that's happening here and that we'd love to be able to explore with others. And maybe that's more of like an artistic route as well for the time being, though there's a lot of people working on interspecies communication, but it's with bigger species.
And it's so important. It's so important that you're doing that, you know, at this stage of thinking about these implications, because we are playing with life. And it's that massive cliche, life finds a way, but it does find a way, doesn't it? I mean, I have to laugh at the fact that a lot of people are really surprised that, you know, oh, they've just found that a female crocodile has had an egg with, it's not actually a viable offspring, but basically the female, you know, that is the whole Michael Crichton, Jurassic Park, the dinosaurs are breeding without a male. And there's so much about the natural world that we just don't know right now, isn't there? Particularly at the scale that you're working with, because we don't even know all the bacteria out there. We don't even know all of these microbes yet.
No. So interesting is that throughout evolution, I mean, life extends in so many strange and weird ways. And you know, at this point in time, it looks like humans are going to have a huge hand in making lots of strange things happen, many of which are probably absolutely awful. But at the same time, it's the reality. And so where do we put the limits? I mean, just cannot answer this in this conversation. But there might also be tremendous beauty to it, right? Like, how do we, if we can kind of think in a specific framework that adopts more of a collaborative stand with other species, you know, is there a way to create wonderful things? I remember when I was a teenager, maybe 12 years old, I was watching Star Trek, one of the old ones, and there's this species that lives in fluidic space, and I think they're one of the enemies, and their whole ship is basically an organ. There's no mechanics inside, it's just grown. And I think that's obviously probably the first point of wow in my life about the possibilities of this. But you know, I think that's where kind of the microbial world is taking us as well. What if we could, and we're doing that already, trying to grow organs, but that's the future of this sort of technology as well, right? We need to be able to create electricity that works in organic environments.
I'm thinking, you know, it's important that you mentioned Star Trek, because many people, I find that not Star Trek, sci-fi is Marmite. People either love it or they really hate it. People are either, yeah, I'm all over it, I've read this, that, and the other person, or they're like, oh no, I don't like sci-fi. Sci-fi has brought forward some profoundly important concepts that, obviously, when you watch that, you probably thought, oh, well, as a child, it would have seemed mind-blowing. Then, of course, you've got, moving on to sort of sci-fi, essentially, Ridley Scott, you know, Prometheus, that whole sort of race. I mean, the last one kind of flipped it on its head a bit. But, you know, sort of the Promethean sort of the movie before, the last one, you've got basically a living spaceship. You've got these highly intelligent bipedal creatures, a weird biology, obviously informed by various sort of parasitic creatures on Earth, but actually working with living systems. And then, of course, you've got Rachel Armstrong, her living spaceship Persephone. For some people, you know, at the time it would have seemed mind-blowing. How on earth can you create a living spaceship? But effectively, of course, if we think to the ISS, it's already got loads of living experiments going on up there. Yes, it's in a metal container, but inside you've actually got these living organisms and experiments. So it's so important to do that. And it strikes me, the other thing about your project, I can see that as you develop this over time, what will happen is that you're probably going to start answering questions for people that you never even imagined your work was going to be relevant to. Because
exciting part.
The world's changing, and we are going to see some really novel behaviors. We're going to see opportunities that we never imagined. And your project is so at the edge. You're looking at something so sort of out there conceptually that when that happens, you are going to be an obvious port of call to ask certain questions. So it's a really, you know, it's wonderful to see the way that you're working and that you are not pinning this down too soon, because there are so many ways this could go.
Well, I'm thankful you're saying it that way. I speaking of spaceships, I also that was one of the things that floated in my mind as well, is that it's obviously kind of these closed environments where it's hard to create electricity, or just like it has to be a whole self-contained system. And I did see potentially like small kind of bioreactors growing bacteria and proteins to be able to make new forms of electricity or components within a spaceship in the future. Because, and I think those are the, like, space travel or military in general are those kind of strange spaces where the more exploratory research goes on, just because we need to potentially be prepared if, or the, like, sometimes they're the most forward-facing places of exploration. It to me, like, because of their capacities and working with humidity, that might be also an avenue.
I mean, in the back of my head, I was thinking DARPA, because a lot of people think about the military in terms of just warfare. But obviously, when a major disaster happens, it's the military that come in. And certainly in my own sort of work, I found that military strategists are some of the most, basically, they're the most open-minded and sassy to the kind of scenarios we might face. They tend to be technically good. So yeah, I mean, I'm sure at one point, if you don't knock on their door, then DARPA are going to come knocking on yours, because there would obviously be some applications going on there. Now, partly because we're in the middle of a heat wave, and I know my phone is going to be getting very hot here, which I have to say is one example of the limitations of electronic technology that is very much prominent in my mind at the moment. I don't know about anybody else, but my phone will start to overheat if it's running on a video for more than a certain amount of time right now. So we've got just time for 2 more questions. You probably know, because you've watched a few of these before. But the first question is, it's mid-century, it's the year 2050. How do you visualize how these fields, biomaterials, biodesign, biofabrication, the convergences across them, how do you visualize that might have shaped our world?
Okay, yes, I should have prepared for these questions, but I obviously, where my imaginary goes directly is, obviously people start being much more aware that this is the future. 2050, that's in 30 years.
Not far.
Yeah, not far at all. People are much more aware of the possibilities of it, and so that now that's where much more of the funding is going. But we're starting to see kind of where I find is very interesting research going on now is in all this kind of metabolic building research. We're starting to create cities that are kind of working like living systems, in the sense that they're very kind of circular, and everything that's going in is kind of being transformed into new things. And I'm not being very eloquent right now, but you know, basically kind of cities starting to work like entire bodies, and that's where I get really interested in as well, and that are starting to really invite other species back in, because right now we're building as humans for humans only, and basically excluding absolutely everything out. That's a massive exaggeration, but I think what we're starting to understand, or what I hope we are, is that we are ecologies, and that's how we function the best. And so how do we, I see 2050 being the start of a turning point where we've started to design not just for humans, but the entire kind of bioregional ecologies that we are in. Hopefully.
Yeah, very much aligned with my own vision. And I think, you know, it's aligned with really everyone that's participated, particularly Richard Beckett, particularly Claudia Pasquero, Ecologic Studio, Rachel Armstrong. There is this connectivity, and it's kind of about 15 years ago, because of the fact that sometimes when you're sort of presenting to a very big audience, you've got to give them something that they can kind of hold on to, that they're going to be familiar with. So I sometimes used to sort of use the analogy of Cameron's original Avatar, because that would get across the idea of, you know, the tree of life. Obviously, conceptually, philosophically, none of this stuff is new. I mean, this is, you know, thank you to the indigenous cultures of South America. You were onto this millennia ago. And I found that people kind of got that. But the difference today is that although back then, 15 years ago, we did have some really kind of seminal works. We had sort of bioluminescent light, and we did have very sort of early kind of energy projects powered by bacteria and things like this. But we had nothing like the number of projects, and certainly nothing like the number of prototypes. today I find that people's minds are just completely blown with the fact that not only is this concept a possibility, but that I can actually roll out a whole series of, well, look, here's one the community did earlier. Here's how it works. Look, here's some footage of it actually doing the job. And I've never seen audiences so excited as when I'm doing that, because this stuff is genuinely more exciting than technology, and it's actually potentially a lot more robust. But I guess, as you know, and this is why your approach to your work is so important, is that there is the capacity for novelty here. These are organisms with their own agency, and so we've really got to be careful how we're handling them. The final question.
Yes.
You have one wish. Genie pops out of a lamp, says Paige. It can be for your own research project, Electric Skin, for the whole community. What is it and why?
Oh no, this is so hard. And I usually love these questions. Let's see, I have one wish. Okay, well, I'm just going to go with, you know, a massive amount of funding and a massive community working around this concept of electrically active bacteria. And, you know, our energy future is grown, not extracted. This is, and we have kind of, we are working with bacteria in a capacity that somehow we've communicated with each other that that's okay, that we're using them in that way. And we are kind of living in kind of structures that are coded with this technology, and we're living in that world.
That sounds great. And as you said that, it did actually strike me that up until this point, although bacteria and microorganisms have, as it were, we don't know if they're conscious, but they have certainly been aware of their, as it were, intervention in our biology and in the environment, because they have actively sought out these new host species, these new environments. They've migrated. So they've shown their own agency, their own capacity for decision making, however that is operating in their sort of collective brain. We're now at the cusp, because this is humans actually recognizing that and saying, now hang on a minute, we're going to express our agency. We're going to start to actually think about how we work with you. We might not get it right all the time, but I think it's a seminal moment in human history, because although when you look to the past cultures, certainly they have spoken to the environment having agency, they've spoken to a consciousness, they've spoken to an intelligence and sophistication. It's not the case that until now humans were actually looking at pathogens and thinking as strategically. Probably the closest we've got to that is people thinking about their gut microbe and kind of how they might try and benefit their health through eating probiotic yogurt or whatever. But I think this is incredibly exciting, and I think you're at the edge. So I'm really delighted that you have participated in this series. What I really want for us now, I want a big gathering. I want a massive gathering with all of those people that participate in the series, and with all the people that we collaborate with, all of our other co-creators, so that we can actually show the world in a really coordinated fashion that this is what this has to offer. So out there, I'm sending that out to the universe. Hopefully sooner, not later, that will happen. Thank you for joining us today. Tomorrow we will have the last session in the series. We're going to have Rosie Broadhead, and Rosie's work looks at how we can use biomaterials to address issues of human health, and from a slightly different angle, but kind of, again, there's a synergy between your work, as there was with Veronica Rana's work. So join us tomorrow. It's going to start an hour earlier tomorrow with that session. I really hope to meet you and your team in person before long, and the absolute best of luck to you with your journey. And Imperial should be speaking with you. they need to be working with you here. That's got to happen. Bye for now.
Have a lovely evening and good heat wave.
Take care. Bye bye.
Yeah.
Connect that.